Okay, so I have a feeling this video might be a little long, but that's the good news when you're watching video lecture. Please feel free to pause the video and take a 15-minute break. It really does help keep your brain active and you can get more out of the video. We're going to be going through quickly all of the probability rules, and then part of this video is how to apply them to word problems. And a video upcoming, it will be how to apply them to actual data table charts. But to remind you, the notes that go along with the video, there's lecture notes. Now on this one, I included a worksheet of the problems we're actually going to do in this video, but I did not include the answers because I didn't want you to look ahead. It makes so much more sense if we can just do each part at a time. And then I included the first 2 pages of what I call worksheet number 1, even though the entire worksheet and answer key is in the probability module on Canvas. You don't have to pull that up right now, but I included the first 2 pages, and that relates to part of your homework is to do worksheet 1, number 1 through 13, which are the 2 pages I put in this handout. And again, answers are on Canvas. Do number 3, but there's a second part to number 3, and it talks about an unfair die, and the problem's not even about a die. That is a typo, so you can just knock that out. You are to do the book homework, chapter 28.3, whatever I have listed on the homework sheet, and then read chapter 28.4, because again, it always makes the next video go so much better if you've already read once. All right, so let's start into lecture notes. Oh, I apologize. There's definitely one more thing I wanted to mention. I am trying to make the probability unit a tiny bit easier. So on worksheet 1 that I included in the notes, I have permanently deleted 2C, 9B, and I made a comment about number 6. So please follow that. The document that's on Canvas will not have those marked out, but you are not to do those. So this is the most updated version of worksheet 1. Okay, so chapter 28, probability rules. Well, in chapter 28.2, we're going to cover the addition rule. Okay, so unfortunately, the way we talk in our real life as humans is sometimes does not match up to mathematics. Like this word or. If I told you that I was going to go to Walmart or Target tomorrow, you would probably make the assumption I meant one or the other, that I wasn't going to both. Unfortunately, that's not what the word or means in mathematics, probability. So I'm giving you notation, definitions, and the words all at the same time. So A or B. Or is denoted by the big U, and it's called the union. So A or B equals the probability of A plus the probability of B minus the probability of A and B. This is the intersection, and it's denoted by the upside down U. This is always presented originally as a Venn diagram. You know, we'll put A here and B here. So A or B. So if I color in A, and then if I color in B, look what happened. I ended up double counting the intersection. The intersection is where both occur, right? I do want to count the intersection, but I don't want to count it twice. that's why we subtract it off. So basically, A or B is what I call the entire snowman, including his middle, including his belt or his waist. A or B or both. Okay, so that's what it means in probability. We actually have already done the addition rule. I didn't necessarily tell you we were doing a fancy probability rule. When we did the rolling 2 dice, the sum of 2 dice, on that first handout at the very beginning of the probability unit, and I think we said, there was some example, I don't know, what's the probability you rolled a sum of 7 or 8? So we went and we added up the probabilities for rolling a sum of 7. Then we added it to the probability of rolling a sum of 8, right? We just added them. We didn't have to worry about this term, right? Because you cannot be a sum of 7 and a sum of 8 at the same time. There was no intersection. That actually has a vocabulary word. Well, it has 2 of them. We have 2 synonyms. When you have 2 events that cannot happen at the same time, it's called mutually exclusive, or it's called disjoint, meaning that intersection term is 0. Because there is no intersection, you cannot happen at the same time, right? You can't be a sum of 7 or a sum of 8 at the same time. We're talking about cards. You cannot be a king and a queen at the same time. But you could be a king and a heart at the same time. Those are not mutually exclusive. So let me write that up a little bit. Okay, probability of king or queen. There are 4 kings in the deck. There are 4 queens in the deck, which makes a total of 8 distinct cards because you cannot be a king and queen at the same time. You can put that in your calculator if you want the decimal. But what about this? Oops. So we were sorry, I know you can read, but we're picking 1 card from a deck of cards. So what about if it asked a king or a heart? Well, there are 4 kings in a deck. There are 13 hearts. That's the suit with the red heart on it. There are 13 cards that are a heart in a deck of cards. But there is an intersection. It's called the King of Hearts. The King of Hearts, right? So think about it. The King of Hearts was counted here. The King of Hearts was also counted here. If you actually got out a deck of cards, and I really recommend doing this when you're teaching this to kids, pick out all the kings, pick out all the hearts, have them count how many cards they have. And they are not going to have 17 cards. They're going to have 16 cards. So that's a very tangible way to get them to understand that they only have 16 cards that satisfy that criteria. So that's the classic addition rule, because king and heart is not disjoint. King and queen is disjoint. All right. Another rule that we already use when we're doing that dice problem, the sum of 2 dice, that handout we had at the beginning of the unit. We're going to give it a formal name now. I'm still in chapter 28.3. is the complement rule. I'm trying to use the notation your book uses. Unfortunately, there is tons of different notation. So this is a plus a prime equals 1, just splitting up that unit whole. I can tell you when we get to our word problems, the language you're going to hear me use of how to apply this to our word problems. One minus what I don't want equals what I do want. And that 1 is coming from that unit whole. When we were doing that dice problem, I think it was a sum of at least 3 when we were rolling 2 dice, and I didn't want to have to add up the 3 and the 4 and the 5 and the 6 all the way up through 12. We knew all of the probabilities added to 1, so we said 1 minus, the only thing I didn't want was the sum of 2. So that's how we approach that. So we have already applied this once to the sum of 2 dice problem. Just a moment. Okay. I'm sitting here hesitating if I even want to show you something. Don't write this. This is why I did not put it on the notes. Your book is using the prime for the complement. Like if I know there's 40% boys at JMU, there are 60% girls, right? That's all we're talking about here. So don't write this, but that complement, the prime, some books use a T, some books use a dash, some books use not A, some books use squiggle A, and there's probably even more than that. So unfortunately, I don't know why, there is so much notation that shows the complement. We don't have to worry about that. All we're doing is figuring out how to apply this to my word problems. And that's going to be probably the most important thing. Okay. Before we get to the last rule, we have to talk about another sort of definition, something called dependent events versus independent, but it's easier to discuss dependent. Basically, it means they're related, if you want the quick definition. Okay, 2 events are dependent if knowing one thing happened first affects the probability of the second thing happening. We've actually already done this. Remember when we did the tree diagram of picking different colored balls out of the bag? And the specific example of without replacement. So then when we did that second branch, if originally we had 10 balls, then the second time we picked a ball, it was down to 9 balls. So we had to make our fractions out of 9 instead of out of 10. That's because if you're picking 2 balls from a bag, one at a time, without replacement, depending on what I got on the first pick does determine the probability for the second pick. So we've already kind of handled this just in a very tangible way when we were making our tree diagrams. Okay, so I underlined it 10 times, right? If your two events are independent, then that intersection term is just the two things multiplied. Now, if they are dependent, we're going to cover that in another video. I can tell you the word problems we're about to do is all assuming independent. So you're going to see we start multiplying everything. Now, at this point, you might think I've contradicted myself because a minute ago, I talked about picking the balls out of the bag without replacement, and I said that was dependent. But if you remember, we did multiply the branches at the end, right? But we were allowed to do that because the first branch was out of 10, and then we made sure to make the second branch out of 9. So we had already taken care of the issue that the probabilities were going to change. All right, so now we're going to start doing these problems again. You're going to have to write these on another piece of paper or something, right? There's definitely not room to write on this piece of paper. These are all extra problems, so I don't have to steal from the worksheet 1 quite yet. This is the stuff you guys really don't like. I'm going to try to show you the best way to stay organized that I've found from years of teaching this, because I teach this in all of my classes, that's really going to help you. So I know a lot of times when y'all watch my lecture notes, I do a lot of steps and I do a lot of organization, but when you go to practice your homework, for some reason you feel like you can skip steps and not use the organizational tools, and that's how you end up getting very confused. So, number 1, about the fire department. 85% of its calls are for medical assistance, and we're going to look at the next 2 calls. So first of all, let me just start here. Anytime they give you a percent, you have to turn it into a decimal. Probabilities are numbers less than 1. That way, you can never multiply percents. You can multiply decimal forms. MA is for medical assistance. Couple things here on this one. Think about, we don't call fire departments, right? But think about calling 911. Most phone calls to 911 throughout the day are absolutely independent, right? Lots of people who have nothing to do with each other need help. Now, if there's one accident on the road, yes, in a 20-minute time frame, you know, the phone calls are going to be related to that. But in general, throughout a day, different calls have nothing to do with each other. Also, going back to definitions I gave at the very beginning of the unit, this is the empirical probability approach. The fire department has no way to just like flip a coin or roll a dice to figure out its probability, right? You can imagine that the fire department has a log of all of its calls that's gone on, let's say, for the last 5 years. And when they look back, they can say, wow, 85% of the time that we go out, it's for medical assistance. Now, that does not guarantee that for the next 20 calls, exactly 17 are going to be for medical assistance. We talked about that long-term probability, so really that is definitely a long-term, long-run probability. Part A is just making sure you know that when the problem gives you one probability, you can immediately go write the other one. What's the probability a call is not for medical assistance? Well, 85% is for, 15% is not. There's only 2 choices in all of these word problems. You're male, female. Calls for medical assistance or it's not. You remembered something, you forgot something. You have a gas stove, you have an electric stove. There's only ever 2 choices. There are not more than 2. All right, now we're doing our 2, I'm sorry, I didn't write that. Our 2 calls, right? Probability both are for medical assistance. So, you know, the other day when I was doing the tree diagrams, I was trying to foreshadow, hey guys, we're not going to be doing tree diagrams anymore. They're just going to ask you one specific thing. So I kind of showed that dash method. I mean, honestly, on this one, you could do a tree diagram if you wanted. You definitely would have to label the branches. But there's no need to. So this is what I call the dash method. So the first call has to be for medical assistance, and the second call has to be for medical assistance. I'm really trying to stress that A-N-D, because and means to multiply. That's our multiplication rule. So I have my two. First one's for medical assistance, and I need the second one to be for medical assistance. So I'm going to put in the 0.85 times the 0.85, and oh my goodness, did I forget my calculator? All right, I forgot my calculator, and if I stop this video, it won't keep going, so give me 30 seconds. Okay, I just ran across her house looking for my calculator, and I got it. Let me catch my breath. Okay. Sorry, guys. But you can put that into your calculator, right? 0.7225. Okay. Part C and D, I actually want to do at the same time. Read C and D. They're very similar. Make sure you can catch the difference. And we did something similar in the middle of our tree diagrams. So part C says the first is for medical assistance and the second is not. I have no confusion. They told me exactly what's going on. Some students call this specific, distinguishing order. I'm not confused. You told me exactly what you wanted. I can just do it. Okay, I'll calculate that in a second. But look at part D. One of them is for medical assistance. Well, see, now I'm a little confused. I don't know which one you mean. Did you mean the first one was for medical assistance and the second one was not? Or did you mean the second one was for medical assistance and the first one was not? There are two very different scenarios that satisfy the same criteria. Now this and this are not happening at the same time. There is no intersection. But here's our addition rule. It's kind of like I can take Highway 81 home or I can take Route 11 home, but I can't be on both roads at the same time, right? So this right here is probably the shortest example to try to highlight to you, when do we multiply and when do we add? You always multiply within the case. But if there are different cases that satisfy what part D asks, then you add between them. So now we can just put in our numbers, and let's make sure we know that this number is the same as that number. Repeated addition is multiplication. I have two of those things, right? Let me get some numbers for you. Okay. So take a minute. This is the shortest problem I can do to try to show you what's going on. All right. Let's go on to number 2. I'll try to up it a little bit. Oh yeah, here's one of my famous problems. You'll even see them on Worksheet 1. This was from a book. It was all about this girl named Jeannie, and she has to make her to-do list or she forgets what she's doing, and she has a bunch of chores and da-da-da-da-da. So they do tell you in the problem that the probability she forgets any chore is 10%. That was given, right? Now immediately you can go ahead, so that's the given part. immediately you can go ahead and write the other one. If there's a 10% chance she forgets, then we must know there's a 90% chance she remembers. Because you never know as we start working through the pieces if we're going to need to, use the 0.1 or the 0.9. All right, she's got 3 chores. What's the probability she forgets all 3? You're welcome to do the dashes. I just want to show you a different organization tool because you'll probably see it on my answer key also. She has to forget the first, and she has to forget the second, and she has to forget the third. I kind of like this because from algebra, if you have variables sitting next to each other, it means to multiply, right? So I don't have to sit here and use the multiplication symbol. So 0.1 times 0.1 times 0.1. Forget, she has to forget the first, and she has to forget the second, and she has to forget the third. Please know that repeated multiplication is to a power, right? Because some of my problems are going to make you do something 20 times. Nobody's going to type in 20 different multiplications into the calculator. You're going to use the power function. Make sure you know it's like the little caret. I guess some of you use the, gosh, I don't use it. I don't know. I think there's a Y to the X button on the calculator or something. I just use the caret. Okay, so that's the probability she forgets all 3 if she has 3 chores. All right, now let's make it more complicated. Part B here is where we start students not liking this topic. I'm going to convince you, since this is our first one, right? I'm going to take the time to convince you that you do not want to do it the long way, that you have to learn the shortcut way. So we've got 3 chores, and part B says remembers at least 1. Okay, you cannot not read the word at least. So many students just gloss over that. Here's that word that you guys don't like, right? So the first thing is you have to think about, what are they asking me? Remembers at least 1. All right, well, this is where I really recommend, some students call this a T-chart. I call it a table. Let's say you're my roommate. No, I'm your roommate. And you're Jeannie. And I knew you had 3 chores to do. And you come home and I'm like, Jeannie, you had 3 chores to do today. How many did you remember? So I'm asking you, how many did you remember? You could have said, oh, I remembered 1 of them. Wasn't a great day. You could have said, I remembered 2 of them. Not a bad day. You could have said, I had an incredible day. I remembered 3 of them. Most students forget this. You could have said 0. You could have said, I remembered nothing. I had a terrible day. I'm going to bed. Don't talk to me, right? So this is the first confusion. Some students view this as 4, and they're like, you only had 3 chores. This is not chore number 1. This is not chore number 2. These numbers are representing how many out of the 3. Did you remember 2 of them? I wonder which 2 if you say yes. Do you remember just 1 of them? I'm still going to ask you which one. That's not chore number 1. So here's the problem. Well, all probabilities add to 1, right? So this is that organizational tool I highly recommend you use. Because, now, let me come over here, because I did say I was going to convince you that this is too long. You may have said, oh, that's remembers 1, remembers 2, remembers 3. You might be saying, oh, there's only 3 things. Why does she keep saying that's too long? Remembers 1. Which one? Did you mean the first? Did you mean the second? Did you mean the third? Remembers 2. Which 2? Remembers 3 is the only thing. So really, there are 7 different things. You'd have to calculate that and 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 then add them all up. So that's me convincing you this is too much work. You are not going to approach it what I call directly. This is how you're going to approach it. We're going to circle. Remembers at least 1. Circle what the problem is asking for. And label it if you want, like that's what you wanted, right? That's what the problem is asking you for, the want. That is too much work. I circled multiple things. So this is coming back to the complement rule that we did on the dice problem. That's why I started with the sum of 2 dice on that first day, because this is the first spot I start to lose and confuse students. If these 4 numbers, these 4 probabilities, I wish I knew what they were, right? But if these 4 numbers add to 1, and technically I would love to know what those 3 are added up, I can approach this the complement rule. 1 minus what did I not circle? 1 minus what I did not want will give me what I do want. Remember we said the complement rule is 1 minus what I don't want will give me actually what I do want. So make sure you're understanding that, because this is the guy I did not want. So I'm going to take him away from 1, and when I do that, it will give me what those 3 probabilities would have been if I had added them up. I did not start you with the easiest problem I could have. 0, remember. Here's the problem. If we were in class, you would see me dramatically sigh at you right now. I don't think that's going to work from just listening to my voice. 0. We can't do nothing. In the classroom, I stand there and stare at you for 30 seconds. How do I show you nothing? You can't raise things to the 0 power. Anything to the 0 power is 1. That is not helpful. Let me also, before I keep going here, this little title right here is really important. You have to, no pun intended, you have to remember that this problem was asking you about remember. So that's why I wrote the word remember right there. 0, remember. It is synonym time. We have to say it, 0, remember, in a different way. If I remembered nothing today, what really happened? I forgot all 3. See how those are just synonyms? It's the same thing. I didn't change the problem. Forget all 3 is the exact same thing as 0, remember. But I can calculate this. Actually, I think I already did calculate it on part A, right? Okay, so that's your final answer. All right, let's do part C. So part C remembers the first but not the second nor the third. Wait, I feel like they're telling me exactly. I don't even have to think. Remembers the first, not the second nor the third. That is specific order. I want to make sure you don't overthink the easy problems. 0.9 times 0.1 times 0.1. The ones that they are being so specific on, super easy. So that was an easy one thrown in to give you a tiny brain break. All right, now we're getting her up to 6 chores. Forgets no more than 5. So as soon as you start thinking no more than 5, that's like 5, 4, 3, 2, 1, 0. I'm feeling very overwhelmed. It seems like there's a lot happening here. So I'm going to my organizational table. This part D is about forgetting. So I'm going to put the number F there. You can, if you want, you can list the numbers 0 through 6, but I promise you, all you have to do is list the first 2 and the last 2, and that will be enough to keep you organized. So no more than 5. That is 5 downwards. And I'm going to label that. That's what the problem's asking me for. Yeah, too bad I don't know what any of those probabilities are. If I knew what they were, I'd add them up, I guess. But I don't. And actually, it's probably 3 or more videos from now, I don't even teach you how to calculate that stuff until the end of the probability unit. So really, at the present moment, this is going to be impossible for you to calculate. Your only hope is the complement rule. And if you have stayed organized here, you should be able to read the complement rule straight off your chart. 1 minus, what did I not circle? 6 forgets. See, that's why that title is really important. Forget all 6. F, 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 F. 0.1 times 0.1 times 0.1. I'm getting a little lazy here. Now, this is also depending on your calculator. Let me show you, if you have a TI-83, what's probably going to happen. Well, the light's terrible. You're not going to be able to see that. If you put in 0.1 to the 6th, you're going to get 1e to the minus 6. That is scientific notation. You have to know what that means. So if you're not good on scientific notation, you need to make sure you do a few examples. 1e to the minus 6. Here's your decimal. 1, 2, 3, 4, 5, 6. So really it's 0.000001. I only require 4 decimal places from you. 1 minus approximately 0. 1 minus approximately 0 is approximately 1 or 100%. Okay, so how your calculator is going to show that, it really depends on what calculator, so I need you to practice that right now to make sure you understand that that is approximately 0 to 4 decimal places, so 1 minus 0 is 1 or 100%. All right, let's go on to number 3. I think this is similar to something on worksheet 1. Now, number 3 looks so short and easy. True-false test, 10 questions. They didn't give me a probability. The other 2 problems did. So there's going to be a few that don't give you the probability. True-false is one of them, because we do assume you know that on a true-false, the probability you get it correct is 50%. There is the assumption that you know that. That is why they did not give it to you. There are 10 questions. Randomly guessing, meaning you know nothing. Pretend it's in a different language. You get at least 1 wrong. At least 1 wrong. At least 1 is 1 or 2 or 3. I'm feeling overwhelmed. So let's put the number wrong here. All you have to do is show the first 2 and the last 2. I went up to 9 and 10 because it said 10 questions, right? Okay, at least 1. This is actually what the problem is asking me for, to add up all those probabilities that I have no clue what they are. And again, impossible on this video because I haven't taught you how to do that. Complement rule is the only thing you have. 1 minus, what did you not circle? 0 wrong. See, that's why that title is so important. This was not correct. This is wrong. 1 minus 0 wrong. That's my sigh. It's the 0 case. You can't work with the 0 case. Anytime you see the 0 case, you're going to have to take 1 extra step. It's synonym time. If you got 0 wrong, you really got all correct. When, remind yourself there's 10, all 10 correct. So you could put 10 check marks if you still need to show your dashes, 2, 4, 6, 8, 10. At some point, you probably won't have to show your dashes anymore. You can kind of visualize, oh, I've got 10 corrects in a row. 0.5 times 0.5 times 0.5. 0.5 to the 10th. This is a fairly unique numbers. I'm showing you more than 4 decimal places just to make sure that you put it into your calculator correctly. There's probably a lot of wrong ways to just get like 0.999. So on these problems, I am absolutely not just grading your final answer. You have got to show me some work like this and then this, because there's lots of wrong ways to get the correct answer. All right. Let's do number 4. Number 4, I didn't put it on here, but this is my real life. So every single year, hold on, let me take a sip of my drink. Every single year at JMU, faculty can enter a lottery to win $500 towards any technology they want to buy for their personal life. And it all depends on how many faculty actually enter the lottery. And if you've won somewhere in the last 5 years, you're not allowed to enter. So some colleagues of mine have made a fairly good guess as to what is the probability of winning the lottery. So we feel like, I mean, it might only be an 8% chance, but I'm going to run it 10%. So the probability that I win the lottery is 10%. What is the probability I lose 15 years in a row? Because guess what, guys? That's exactly what has happened. Every single year, I stay so positive, and I really think it's going to be my year to win the lottery. There were probably 5 years I kept using my old computer thinking, no, when I get the money, I'm going to buy the new one. Well, last fall I lost again. It was my 15th time, so I had to just go buy myself a new computer anyway. Every single year I am hearing about my colleagues who win. Sometimes, actually, I'll have 2 colleagues who are married and they both win in the same year. Sometimes a brand new faculty member will win. See, I'm pointing this out and I'm rambling right now because when it comes to probability in mathematics, we all have emotion, but we can't stop at the emotion. We can have the emotion, but then you have to keep going to actually do the mathematics. My emotion is, I think I should have won by now. I think I'm due to win. And I have those emotions, right? But I know how to do the mathematics to actually figure it out. So let's see, is this such a unique thing that's happening to me? Do I have such terrible, terrible luck? Well, lose 15 times in a row. So if you want, I'll do it one more time. You could put your 15 L's. What is L worth though? What is lose worth? Win is 10%. Lose is 90%. I lost on the first one, 0.9, times I lost on the second one, 0.9, 0.9, 0.9, 0.9, 0.9 to the 15th power. See, once I do the math, I realize I'm not that special. It's not that the world's against me. There's basically an over 20, close to 21% chance that I would lose 15 years in a row. It's not like it's only like a 0.5% and I can say, oh my gosh, poor me. No, see, when you do the math, then it makes me have to shut up and not whine about my life. All right, let's do another one. Tried to shorten up a really long book problem. Basically, it was talking about calling an airline to make a reservation. So I'm sure a lot of people call the airlines, they don't actually make a reservation. They're just trying to get information or something. So, to, let's say, make a booking. 30% of the time, a flight actually gets booked. Okay? And we're going to look at the next 20 calls. So as soon as you read, 30% chance that you're actually going to make a booking, remember, the not make a booking, we already know is going to be 70%. All right, what's it asking? Part A, more than 19 make a booking. So I think I'll just call that make. And I think on this one I'm going to want to put A and B up at the same time. So I'll put the little line to keep me organized. Now, if you're in a good habit of doing your little chart, let me show you what's going to happen here. This is make. All you have to do is show the first 2, 20 calls, and the last 2. And you're like, okay, more than 19. Wait, more than 19 is only 20. So if you're doing this and you circle, make sure you know, wait a minute, I didn't circle a bunch of mess. This is not a 1 minus. I only circled one thing. I know how to calculate that one thing, right? This is 20 make a booking. You could put 20 check marks in a row. 0.3 times 0.3 times 0.3, 0.3 to the 20th. So this is absolutely not a 1 minus. Just because the word more than is there does not indicate to you if you should be doing a 1 minus. How do you know if you're doing a 1 minus? If you circled a bunch of mess. I didn't circle a bunch of mess. I only circled one thing here. Oh, yeah. Please put this in your calculator, because let me tell you something I will take off big points for. That is not the answer, okay? Scientific notation. I have some students who don't even see the e to the negative 11, and they try to tell me it's 3.48. That is absolutely not correct. Probabilities run from 0 to 1. When you try to tell me the probability is 3.48, you need to stop and say, wait, that's impossible. Oh, e to the negative 11. You'd have to pick up this decimal and go 11 places. Basically, the answer to 4 decimal places is approximately 0. Oh, this was not the one that I wanted to show both at once. I'm sorry. I hadn't read my own problem. So I'm going to erase this. All right, part B, again, just so you don't overcomplicate the easy problems. Where am I? Part B. Only the first 5 get a booking. Wait, they told me exactly which 5. And if you want, you could put your 20 dashes and make it look like that. They told you which 5. Make sure you understand that 5B does not say the probability 5 get a booking. I cannot ask you that yet. I have not taught you how to do that yet. Only the first 5 is the critical part. They're telling you those 5 got it, the next 15 did not. 0.3 times 0.3 times 0.3 times 0.3 times 0.3. There's 5 of them. But we got to keep timesing, right? Because this is all multiplication. But the x's are worth 0.7. And there must have been 15 of those. What I wanted to show you on this one, most common mistake is for students not to do the 0.7 to the 15. They read only the first 5, made a booking, but there were 20 calls. So a way to prevent yourself from making a silly mistake, look at your exponents. They have to add up to 20. Look at part A that I already erased. You'll see a 20 exponent. Your exponents always have to total whatever, the problem was about. This was about 20 calls. Okay, so this is 1.1536 e to the negative 5. I don't accept scientific notation. 1, 2, 3, 4, 5. So absolutely on this one, you can still call that approximately 0. I just wanted to get you to practice scientific notation one more time. All right. Oh, this was another real life example that I've shortened it up a lot. If you've never played Yahtzee, it's a fantastic game to play. It's like a combination of poker, but with dice all at the same time. You have the scorecard and you have to get certain things like 3 of the same number, or full house, which is 2 of one number and 3 of the other. There's 5 dice there. But I'll briefly show you what the scenario was, but you don't have to have played Yahtzee to answer this question. My daughter, let's see, let me remember how it was. Oh, wait. See, I have my own personal notes to remind me. That's right. Okay, so basically this was her. She only had one more roll. And in Yahtzee, kind of like poker, you can keep the dice that you want, and you can pick up the other dice, and you can roll them again. So she only got one more roll. And she needs, on her scorecard, she needs a 3 of a kind. Now look, she already has 2 of them, right? So this was very real life. We were playing this a couple years ago, and she asked me what the probability was, and I had about 30 seconds to try to get an estimate in my head. We're going to do this precisely, though, because I get to pick up these 3 dice. But then I started realizing, well, if one of those, when she rolls them, is a 5, she'll have her 3 of a kind. But if 2 of them turn out to be a 5, she'll still have her 3 of a kind, right? She would just have extra, but that's okay to have extra. Actually, if all 3 turned out to be 5s, she could still write it down for 3 of a kind. If you're familiar with Yahtzee, that would actually be called Yahtzee, but we're not complicating it. I want to know what's the probability of her getting a 3 of a kind, which means she's going to roll the 3 dice, those 3, and she needs at least 1 5 to come up. I mean, if 2 5s come up or 3 5s come up, that's okay too. And like, at first I'm like, oh my God, I can't go through that many scenarios in my head. I'm down to about 15 seconds, right? My daughter's waiting for the answer. And I'm like, oh, this is exactly what I teach in class, right? How many 5s? She maybe doesn't get any, and then she loses 1, 2, or 3. Okay, at least 1. This is what I wanted. And I didn't have time to calculate all those probabilities. And I'm like, wait a minute, I can go 1 minus no 5s. Oh, there's that 0 case. So 1 minus all, well, not 5. Think about it. 1, 2, 3, 4, or 6 on the dice, right? Not a 5. She can roll a 1, a 2, a 3, a 4, or a 6. So all 3 dice have to be not a 5. They can be any of the other numbers. And that turns out to be 0.4213. So this one gets a little confusing to talk about because we're not only counting up how many 5s, but the actual dice have numbers on them. So granted, you may have to back up and listen to this one more time because I know it is complicated. And that's why at one point I wrote FIVEE. Sometimes that helps you remember those are just the faces. But these numbers are how many of the dice are showing a particular face. All right, let's do a book problem. I love this book problem. And I think it's one of your homework problems. Let's see, I have it in front of me. You can always look it up later. Suppose there are 3 crucial components on a space shuttle. There's the rocket system, there's the guidance system, and there's the communication system. Suppose also the probabilities that the systems function correctly. So they're giving you the, like, what I call okay, that, you know, everything's going to be okay. For rocket is 0.95. For guidance is 0.9. For communications is 0.99. So that was given. And the question is, if 1 or more break, the launch is aborted. And then it asks you, what is the probability that the launch will be aborted? Which is the probability, hey, you know, if I put this on a test, I'm probably not going to say 1 or more. I'm probably going to say at least 1. At least 1 broken. That's the definition of the launch being aborted. It says if 1 or more breaks, we don't do the launch. Okay, so if at least 1 is broken, we are not sending the rocket up. Oh, at least 1. See, at this point, you probably are hopefully getting used to anytime you see at least 1, it means it's too much work because really, that's what it's asking for. And I don't know what those probabilities are. We're not going to come at it the long way. Let me do my complement rule. And I can't stress this enough. This title, 1 minus 0 broken. Oh, and it's the 0 case. I have to sigh again. I have to do a synonym. 0 broken are all okay. Now, up until this problem right now, I would have just raised something to the 3rd power. The reason why I love this problem is they didn't give you the same probabilities. So we don't have the luxury of just raising to a power. We need the rocket to be okay. and we need the guidance to be okay, and we need communications to be okay. So we're not allowed to just raise something to the third power. We just have to actually multiply the 3 okay probabilities. And that turns out to be, who knows? I'll put in my calculator. Oh yeah, 0.1536 is the final answer. Make sure you don't forget the 1 minus. All right, let's see, what else did I have? Oh yeah, I wanted to do, I think I'm just going to do worksheet 1, number 7. We can always do number 6 in the future, not a big deal. You should do, again, the homework I assign. But worksheet 1, number 7 is one I get asked about a lot. And granted, the way it's worded is a little confusing. This is why I always make sure I do it at the very beginning. So this worksheet 1 was part of the notes for this packet, right? So we're doing worksheet 1, number 7. It's very short. When rolling 2 dice, what's the probability it takes exactly 5 rolls to roll a double? So there's a lot implied in here. Think about when you're playing Monopoly, and you know how you get stuck in jail and you have to roll a double to get out, and if you don't, you keep sitting there and sitting there. Honestly, on Monopoly, I think after 3 times you get out anyway. But go with me here. It takes exactly 5 rolls to roll a double. So this is saying, hey, you got a double on the 5th roll. Well, then what happened on the first 4? Well, apparently you didn't get a double. You did not get a double, and 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 finally on the 5th roll you got a double. So this was a very tricky way to try to get you to see precise order. Now the other part of this is they didn't give me any probabilities, but again, this is why I did that dice handout at the beginning of the unit. How do we get a double when we're rolling 2 dice? Well, first of all, remember there are 36, not 12, 36 ways to roll 2 dice. What is a double? 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. There are 6 ways to get a double. So now I know that's that probability. I think on my answer key I reduced it. That tends to confuse students, so I'm going to leave it like this. So you can see, yeah, 6 out of 36. Oh, okay, then not double are the other 30 ways. Now you can calculate this out however you want. You know, raise that to the 4th power times that, and you will end up getting 0.0804. Alright, so that was a lot to take in. This is the stuff, again, that my students really struggle with. You need to use the answer key to worksheet 1, sometimes even in a backwards way, figuring out where she get that, where she get that. Rewatch the videos at some point, and some students find they have to do worksheet 1 like 4 times, but at some point you're going to start to see that all the problems are pretty much the same. All I do is change context and I change a number, because I'm pretty limited by what I can ask you right now. Now, you know, towards the end of the probability unit, once I teach you more stuff, it opens up more doors. But right now, I'm very limited by what I can ask you. So once you do the problems over and over, you're going to start to see the patterns that really do exist. So make sure you start on this early. That way, if you have any trouble, you can email me, come to WebEx, all of that good stuff. All right, see you next time.